Swayam Prabha. Digital India. Educated India.
The next presentation will be from IIT Madras from Microsoft.
A very good afternoon, everyone. My name is Swayam Prabha. I'm from Microsoft, and I am presenting the topic on Connected Traffic Management System, that is CTMS. We have done collaboration with Arpana Alka from IIT Bangalore and Jyoti Prakash Sahu from UPEC Technologies, and Webull.ai is the MD of that company. So this whole project was partnered with Bhubaneswar Smart City Limited of Bhubaneswar, where we had installed cameras in certain places to have an observation about how our model is performing. So this whole solution is about optimizing the green light so that there is a smooth process of the traffic. So let us look into some of the bigger problems that are being faced by everyone. I belong to Bangalore, so you can understand how the traffic will be. Okay, and if it is raining and if it is during the congested hours, like during the time when all the offices are over, it is unimaginable. It's not possible to cross any signal. Okay, so that time these kind of solutions will be a boom. How it will be optimizing the green light signals. So definitely congestion is one of the bigger problem, and we are trying to solve using this artificial intelligence based solution how it will be optimizing the green light timing. This system is also intelligent enough to see how the impact of the days, that is day or weekdays, in the determination of the green light timing. For these special vehicles, yes, there should be some relaxation. If ambulance is there should not be any traffic rules. It should be given, they go till the time the special vehicles are not passing this way. And also, there will be traffic violators. Now, think about this situation, the traffic police is engaged in detecting the violators. What will happen to other players who are in the traffic? So, our system can also do tracking if we use the tracking system. And in every day, there is enormous number of data being generated. Now, think about a year of data, how much bulky the data will be. So, we can do analysis in this as well. So we provide a solution that is Connected Traffic Management System, that is CTMS in short, that will be hassle-free and efficient way of handling the traffic. This is a brief overview about how we have made the solution. So the solution can identify the idle road, emergency vehicles, and also kind of managing the time based on the surveillance cameras. At the particular junction, the solution not only communicates for that particular junction, but also the nearby traffic junctions. That makes it connected. Third is how we are doing this analysis. We are doing a threefold ensemble-based analysis, taking into the account object detection using computer vision, traffic forecasting using time series forecasting, and then optimizing in a weightage-based method to find out the optimal green light. This solution is supported by real-time formulas that we have assigned and can be encapsulated with many other solutions like automated number plate detection and other things which a normal traffic police actually looks into. So this can be a kind of artificial traffic police instead of a manual traffic police. So this is how our solution is looking like. We do have, for each of the lanes, the cameras are installed. There can be one rotating camera which will be looking into all the directions, or each individual cameras for each direction. We can also provide some sensors which will detect the sound for the special vehicles, and then based on this, the vehicles will be counted based on our best models. That is kind of a greedy search that we have done, and then the time series forecasting will be going on. So the data was taken from Bhubaneswar two traffic squares, that is Rupali Square and Ram Mandir Square, where most of the time the traffic is very much congested. The number of vehicles which was detected using computer vision was input into the forecasting engine for forecasting for the next instances or next few days. Why they are done? I'll take next. So we have three pillars over here. First is computer vision solution, forecasting solution, and optimizing solution. In computer vision solution, we are not only detecting the number of vehicles but also the class of vehicles. So we have published a paper, that is CWOT, class-wise object tracking, using the SORT, kind of optimizing the solution of tracking. Each of the number of vehicles which has been tracked will be maintained in our database. That will be input to our forecasting solution, which will be forecasting for the next few days. Now, this algorithm that we have built is not only univariate but also multivariate. That is, we can input external data like weather data or any kind of other data into the forecasting engine, and it will be giving a forecast about how many vehicles will be there for the next period. The third will be our optimizing solution. Now, we have our forecasting done for the next period. We are detecting how many vehicles will be are present in a particular direction of a square based on a computer vision. Now, if there is no variation or very less variation, then whatever threshold or rules that we have designed for a particular junction, it will apply. If the variation is very large, weightage will be assigned. How the weightage will be assigned? It is kind of global optimization of the weightages. I am designing the weightages from the day one. How much weightage or how much error my computer vision is detecting and how much error my time series is detecting. So the weightage will be inverse of the error. So that is how it makes it adaptive for any of the squares or any of the traffic junctions. Initially, will take some amount of days to design the solution for that particular junction. Otherwise, it will not work. Think about the scenario of Indian traffics with the foreign traffics. They're highly variational, right? That's it. Now, for the object detection models, these are some of the models that we have used. SSD10, YOLO V3, Mask RCNN, YOLO V4, faster region convolutional neural network. And for the tracking, we have used CWOT. That is our paper that we have published. For evaluation metric, we have used mean average precision because we wanted to be very much optimistic and greedy in terms of each of the class of Indian vehicles. Now, Indian vehicles do have the property of changing their shape and everything, right? One bus is not equal to another bus. So that's why we wanted to have a class-wise detection. For time series model, we used the whole concept of time series modeling, starting from exploratory data analysis, doing stationary of the data, finding how the data is correlated with the previous lags, so that autocorrelation plots are used. And based on that, we have made a validation of rolling window. It's not like 70-30 or something. It's like 70-30, 80-20, and 90-10. So we have used rolling window so that our stability of the models are there. That is, one best model is selected, and that best model is not same for throughout the year. It keeps on changing based on threshold of retraining of the model. We have used RMSE and MAP as our reporting evaluation matrices. In terms of models, we have segregated the models into bags of models. One is statistical techniques, where statistical time series models are there. Machine learning models, where machine learning models are there, and hybrid models that are ensemble of the models. So, based on these bag of model will be selected for forecasting the traffic. So, we will go for the results and inferences. These are some of the classes of the vehicles that we have, or classes of the objects that we have taken into the account. Cars, bicycle, bus, train, trucks. We have used PT dataset for our standard comparisons, and the data collected from DSCL, installing in two different places, Ram Mandir Square and Rupali Square of Bhubaneswar. So we took around 6 months of time to collect all the data, and it was like, in terms of, I'll say hundreds of GBs, the data was there. So SSDNet was low in MAP. The detection time was low, but it was good in terms of detecting the cars. You can see over there. So the three graphs will be repetitive in coming slides. One will be the MAP of different classes, number of images for time taken, and detection results. So if you see, not only our MAP is important, but also time taken is also important. For example, if one model didn't perform well in the real time, it should be quick enough to retune itself. So over here, if you see, the MAP is less. So one factor is actually less over here. So these are some of the detection that has been done through SSDNet. YOLO V3, that is you look only once. It was far better than SSDNet. Time taken was little bit higher than SSDNet, but it was not that high. That's MAP was far better than that one. So it was kind of better than SSDNet. So it was one of her contender. Masked RCNN, the MAP was far better than YOLO, but the time taken was far larger. So another criteria for evaluation was taken out, although it was far better than your YOLO and SSDNet. Now, the fourth one is YOLO V4. It was not only better in terms of MAP, but also if you look at the time taken, it was very fast. So this was our model which has been deployed in Bhubaneswar Smart City. RetinaNet also we used, but it was not good in terms of timing as well as MAP. And faster RCNN was not better. It was worst among all the models that we have used. Now coming to our second pillar, that is our time series forecasting. We took one instance to showcase how our model was behaving. Now definitely there will be questions about how seasonality factor and everything is coming into the picture. In our time series models, we have one concept that is profiling, that is clustering. We are using not all the models, but clustering of the models. So we have, when the data is seasonal or cyclic, we are using our cyclic or seasonal models for the deployment. Over here, if you see the green box at the end, that is our forecasting period that we have done. So over here, we have used 13 instances of forecast for the future forecast. Here, if you see, we have in the second, first table, that is RMSE comparison. We have used all the models, and from that best forecast and best ensemble are our models that we are comparing with standard models. So you see that best forecast was giving far better RMSE than other models, and that if you see the MAP is far better than other models. It is kind of one-time training that we have done. If you're moving further, these all things will be changing. But in a stability factor, that is one model, if it is selected today, there should be a chance that that model is selected next, based on how the accuracy of performance is looking and how the pattern is looking. So for selecting of the models, we have used stability factor, that is volatility factor. The mean of the accuracies or mean of the error should not be high, and the standard deviation should not be high. I'll move on to the concluding statements. Some of the salient features of our model, that is, it's work fast, extremely suitable to the real-time application. Algorithm can identify custom Indian vehicles because we have trained our model in our data set that we have captured. So we did manual annotation of the data, and that is how our model was able to beat from the pre-trained models. So we have kind of retrained the models. So this model or this whole pipeline is designed to be deployed in edge devices. And what are the problems and how we have got some good answers? During the time when the offices were kind of closing, the congestion was very large in those two squares. So our solution kind of gave an optimal solution about how to give the green light, detecting automatically about the vehicles, number of vehicles. Second thing is how the there are certain instances where even though a particular direction is idle, the green light keeps on moving, or when the particular direction has more number of vehicles, the red light comes into the picture. So our solution was able to optimize the green light and the red light timings over here. In one scenario, during the POC timeline, there was a heavy rainfall, and our algorithm was able to predict and give optimized green light, giving some priority to time series, because during this scenario, the computer vision will be kind of hazy. The detection will not be that much good. So that time our time series forecasting comes into the picture. We were appreciated by Bhubaneswar Smart City for our innovative ideas and solutions. So these are some of the references that we have taken. Thank you.
Okay, so the presentation is now open for floor. Are there any questions? Okay.
So, you showed your testing window, right? So, I just want to know
Okay.
how much testing have you done?
For your computer vision or any of the solution I can tell, right?
Yeah.
Okay. So for computer vision techniques, we use standard datasets for SPT dataset, and over there we didn't go for any rolling window or anything. We simply went for hold or better 70-30 for our selection. And over here we have used stratification because there will be imbalance of the data. When we do the imbalancing treatment, there are many techniques like oversampling, undersampling. We use for computer vision we use GANs, but I believe that we should play statistically. And I have done some research in which if you do stratification of the solution, the results will be far better. For time series, we have used rolling windows 60-40, 70-30, 80-20 or 70-30, 80-20, 90-10 based upon the amount of data.
So, you had those regions coming to you, tested the time series model and every region you said was doing some testing.
Okay, so reasons means okay. So when we do the profiling will tell me what kind of data it is. Now, if I have a straight line ramp signal, that is a kind of growing trend. It's not seasonal over it, but growing trend. Now, if I have a sinusoidal wave, so it is a seasonal, completely seasonal. So how our model is able to give an optimal results, right? Now, in terms of seasonal, let me say sinusoidal wave, it is very time taken and very kind of cumbersome to have all the 40 models running. I can just use a naive forecast. I can find the most correlated lag. I can copy and paste it. That will give me far better result than even seasonal or very long. Am I able to answer the question?
Yeah, I have one question. The performance of the Shibuya and time series prediction will be affected by the weather.
Yes.
So how was it?
Okay. So in certain scenarios that we should, can we go to the last conclusion? Yeah. So in one scenario, we were able to see such in a scenario in the real time where there was a heavy rainfall and was not predicted, right? Because Bhubaneswar does have this kind of peculiar behavior in your weather. Over there, we saw that our time series was getting more weightages than our computer vision because computer vision was not able to detect properly. Okay, so that is the only reason why we have kind of threefold structure of solution. Not only one solution, but most of the time you will see that many devices or many solutions we said they either use computer vision or any kind of sensor based techniques. So we wanted to use statistical based techniques as well.
Whether the speed of the vehicle, whether influence your results?
We didn't went due to the POC time. We didn't go for the speed of the vehicle, but definitely there are solutions where we can measure the speed of the vehicles also. And when we are looking into the traffic, can you go to the video? Yeah. So over here, if you see, sir, then we have a line that is our region of interest. When the vehicle crosses the region of interest, then only the vehicles will be calculated for that particular direction. Even though the detection might be skewed up, some vehicles will be missed out, but in terms of heavy congestion, 100 and 80 are similar than 110.
So once you apply this pipeline of computer vision and time series models, you get forecasts of number of vehicles running on different roads, right?
Yeah.
So once you have this forecast, how exactly do you optimize the signal time?
Okay, so signal time for certain. So over here we have, I think here previous, we have certain rules for each of these, squares. So it's not like that. Let me give an example of Bangalore traffic and Chennai traffic. The rules will be different. So that is why we need a POC time for each of the deployment areas. And in the real time, when you say let me say computer vision has detected 100 vehicles, and time series has detected 10 vehicles. So there is a very much gap, right? So that time the weightages will be given.
Okay.
Now weightages are they are decided from the previous results, how my model has performed in the real time, right? So that is how we will be assigning the weightages to our time series or computer vision solution.
Right. But once you have these forecasts, how do you optimize the segment times? That's what.
You mean to say green light? Okay, green
Yeah,
light.
yeah.
We have done kind of a I'll say bucket of green light. It's like for certain buckets we have given the how much time it will be decided for the traffic junction. Let's say 100 vehicles are there or 100 plus vehicles are there. Then 5 minutes or 10 minutes, and it is different for different regions. Now, whichever zone it is falling, that kind of solution will be given, or that kind of green light will be activated. Right. Now, let me give an example that there are 0 vehicles, right? So 0 vehicles mean it falls to a very minimal bracket. Now, minimal bracket will be like 5 seconds or 10 seconds. Now, real time, if there's kind of a manual circulation, if it is there, then 3 minutes will be designated for one kind of one direction. Now, over here, 3 minutes is very much larger than 5 or 10 seconds, where there is no vehicles at all.
Okay, so there may be a lot of questions, but the time is running out.
So maybe you all can reach out to me if you have any further questions. You can find me in LinkedIn or Google Scholar, or you can message me.